going to a surface area of a rotated parametric curve. So recall, if we have the curve y equals f of x on the interval from a to b, then if we rotate about the x-axis, surface area was equal to 2 pi times the definite interval from a to b of f of x times the square root of 1 plus f prime of x squared dx. And if we rotate about the y-axis, surface area is 2 pi times the definite interval from a to b of x times the square root of 1 plus f prime of x squared dx. So if we want to translate this into parametric curves, note we can rewrite these in x, y, and dy dx. So we have about the y-axis, we would have 2 pi times the definite interval from a to b. Actually, let's do about the x-axis first, since that was what I did earlier. About the x-axis, we have 2 pi times the definite interval from a to b, and f of x is just acting as y. Then we have times the square root of 1 plus dy dx squared and then dx. About the y-axis, we have 2 pi times the definite interval from a to b of x times the square root of 1 plus dy dx squared dx. In our arc length video, so in the previous video, we showed that the square root of 1 plus dy dx squared times dx was just equal to the square root of f prime of t squared plus g prime of t squared dt. If x equals f of t and y equals g of t. So what we wind up getting then, let me actually shift these around to give myself a little more room. The equation about the x-axis, we just essentially swapped out that f of x for y. Our equation about the y-axis, and then we had what we showed in our previous video. So if our x is f of t and y is g of t, we can now just rewrite this entire thing with t's. So rewriting in t, right? We have about the x-axis. Becomes definite integral from t naught to t1. Sorry, 2 pi times the definite integral from t naught to t1 of x. No, about the x-axis is of y. So we have g of t times the square root of f prime of t squared plus g prime of t squared, and then dt. About the y-axis, we have 2 pi times the definite integral from t naught to t1 of x, which is f of t, times the square root of f prime of t squared plus g prime of t squared dt. So now we have two formulas which look fairly similar to the formulas we're familiar with for surface area. It's just now in terms of t, or our parameter, instead of in terms of x. So now for an example, let's find the surface area of the rotational solid formed by rotating a parametric curve defined by x equals 3 cosine of t plus 3 and y equals sine of t on the interval 0 pi about the x-axis. So just a note, this set of parametric equations defines the ellipse centered at 3, 0 with a horizontal radius equal to 3 and a vertical radius equal to 1. Since we're looking only over 0 to pi, this is the top half of the ellipse. So essentially, we have a long, thin ellipse looking at the top half, and then we're rotating that about the x-axis. So it looks somewhat like a football, and we're calculating the surface area. So for this, we have our f of t is 3 cosine t plus 3. So we have our f prime of t is a negative 3 sine of t. G of t is sine of t. That makes our g prime of t equal to cosine of t. We're rotating about the x-axis. So we have that our surface area is equal to 2 pi times the definite integral from 0 to pi of, if we rotate about the x-axis, our formula said to do g of t times that square root. So we have g of t times the square root of f prime of t squared plus g prime of t squared dt. Plugging in, this becomes 2 pi times the definite integral from 0 to 2 pi of sine of t times the square root of negative 3 sine of t, all things squared, plus cosine of t squared dt. Or surface area is equal to 2 pi times the definite integral from 0 to pi, not 2 pi. Definite integral from 0 to pi of sine of t times the square root of 9 sine squared of t plus cosine squared of t dt. This is an integral that you can solve using some trig identities, substitution, etc. So you could do with using trig identities and some substitution. But in general, we can just use decimals to find this. And if I switch over to decimals, here I have my definite integral plugged in, and I have also calculated, the surface area of the sphere of radius 1 and surface area of a sphere of radius 3. So our surface area falls somewhere in the middle, as you can see. So if we translate this back over to our notes, I'll put this back in our notes. We get a surface area of 30.89 approximately. And this falls between, so note, this falls between the surface area of a sphere of radius 1 and a sphere of radius 3. All right, sorry about that. So this falls between the surface area of a sphere of radius 1 and a sphere of radius 3. Which again, our ellipse that we were working with had minor radius 1 and major radius 3. So it makes sense that it should fall somewhere between the spheres of those two radii. So this is our surface area from a parametric, rotating a parametric curve.